first, I'm going to talk about brightest stars we see in the night sky. I guess the talk is going to be divided into two parts. The first to more or less set the scene, talk a little about the astrophysical quantities of stars, not all their properties, but certain aspects that are important for classifying what is a bright star. And then I'll explore over the seasons, the brightest stars of each season. Astronomers rank 21 stars of the first magnitude. The talk will be based on an exercise or a little kind of challenge, so to speak, that I wrote about in the Society's Journal about 2 years ago, where around New Year's Eve, for a couple of weeks either side of that time of year, you can see all 15 of the first magnitude stars visible from Ireland in a single night between dusk and dawn. I mentioned 21 being visible. 6 are too far south on the celestial sphere to be visible from our latitude. They're Canopus, ranked as the second brightest, Alpha Centauri, Alpha and Beta Crucis in the Southern Cross, Beta Centauri, and Achenar, which is sometimes nicknamed Lost in the, or translates as Lost in the River. Essentially, it's part of Eridanus, the constellation Eridanus. But the others, 15 I've put in this table here, Sirius being the brightest, Arcturus, a spring star, and many are familiar names for observers, but sometimes it's nice to know a little of the stories behind them, and that's what tonight's talk will explore. Question we ask is, how bright is that? We can ask is, how bright is that star? It sounds like a simple question, but as we'll see, the answer has evolved over time, has been revised over time, because what we call brightness means different things. The system that amateur astronomers use is called apparent magnitude, how bright the star appears to be in the night sky. It dates back to the time of the ancient Greeks, with the likes of Hipparchus and Ptolemy. Hipparchus drew up a catalogue of over 1,000 stars and plotted their position in the sky, grouped them according to the constellations that they appeared in. These catalogue and the positions in them were the best that they could do with, well, essentially no instruments to have per se. It was very much a naked eye observation. It was best guess as to what position they were in on the celestial sphere. The error margin was quite large compared to modern precision, but they also graded stars according to how bright they were. Hipparchus and Ptolemy called the brightest or bigger stars that they could see of first magnitude, and the faintest they could see with the unaided eye is sixth magnitude. And the rest were all graded at different numbers in between. And it's that system that we use to this day when we talk about stars, apparent brightness in the night sky, or any object's apparent brightness, including, as you'll see here, the scale has been extended since Hipparchus and Ptolemy's time to negative values for brighter objects and higher numbers for much dimmer objects below the naked eye limit. It doesn't initially seem very intuitive because you'd expect negative values to be the faintest object and the higher numbers to be the brightest, but it's actually the other way around. And we're stuck with that system despite what people sometimes grumble about that particular sequence, but it's a system we use to this day. Over time, that system got revised. The first steps in revising it basically came about with the invention of the telescope. Galileo, when he turned his telescope skyward, could see stars fainter than the limit that Ptolemy and Hipparchus had set. In his books, he writes about seeing stars of seventh magnitude or fainter. Then, as instrumentation got better and better, they came along and could find fainter and fainter stars. Ultimately, they had to put it on some sort of logical footing, and that came about in the 19th century with Norman Pogson and others. Pogson is generally associated with the modern magnitude system. He basically had two eyepieces in his telescope and adjusted the aperture of one until he got the star to appear a similar brightness to the kind of reference star he was looking at. And he came up with a logarithmic scale for defining apparent magnitude. Logs were, well, all the rage back then, essentially. So since their invention in the 17th century, logarithms were applied to all branches of mathematics and science, including astronomy. And Pogson, basically, there was a belief that the eye responded in a logarithmic way to star brightness, whereas it's more of a smooth curve than how the eye responds to light. But the logarithmic scale, basically, the way it was established was that a star of first magnitude was 100 times brighter than a star of sixth magnitude. So it's basically goes in steps in a logarithmic way, and the system Pogson determined that the faintest star the human eye could see was sixth magnitude. He again used that technique of adjusting the aperture of his telescope until he got it to approximately the equivalent of the diameter of the human pupil at night. And he observed how faint a star he could see through that, and he called that sixth magnitude. And everything was offset from that. And the system then ultimately got got revised based on Pogson's initial basis. Pogson was an interesting character. He didn't spend much time in England working as a professional astronomer. He spent most of his time in India in Madras Observatory, and he basically kind of argued quite a bit with the powers that be back in London. He pleaded many times for assistance to help him reduce observations, but he was never really sent anyone to help him out. And he got more and more embittered by how he was being treated by the Astronomer Royal of the time, which was George Biddle Airy. Eventually managed to oust him from his position, and unfortunately there's not a lot known about Pogson's life, but we do know that the system he devised has played a crucial importance in astronomy to this day. Of course, now that we've come up with this apparent brightness of stars, it was soon realized that some stars were further away than others. and therefore that affected how bright they truly were. So we had to come up with a new way of determining brightness. How bright would they be if they were at a specific distance, all at a specific distance from the Earth? Of course, to do that, we had to figure out just how far away they were. Now, to achieve that required a few things. One of them meant uncentering the Earth, taking it out of its exalted position as the center of the universe. Once you'd done that, you had to determine what was the diameter of the Earth's orbit, or the radius of the Earth's orbit. And then another thing they had to do was there was still some, well, although the idea of a crystalline sphere had been shattered, at the time they first began to think about star distances, there was still a belief there that stars were just where there was holes in the celestial vault, letting through the light of heaven beyond. So there was quite a fundamental and paradigm shift in human thinking required to be able to work out distances to the stars. The technique they were going to use was parallax. It was already well known in terrestrial surveying. It's a trigonometric way of measuring distance. Basically, it's very akin to holding your finger out, lining it up with a distant object, and alternately opening and closing your eyes. And your finger appears to jump back and forward with respect to the object you had initially lined it up with. And what's happening there is you have your baseline, which is the distance between your two eyes, and you're trying to measure the amount of jump, and from that apply trigonometry, work out the angle of the jump, and then if you know the distance between your two measuring points, you can work out the distance to your finger. In this case, rather than the distance between your eyes, you're looking at the Earth's position in June, and then 6 months later where it is, and that's giving your initial baseline of the triangle. You observe a star and look at how much it's going to jump back and forward with respect to more distant stars, and then measure that angle and half that angle, and therefore you can derive the parallax. But these measurements are really small, even using the diameter of the Earth's orbit as a baseline. You're looking at such a fraction of a degree that, like, we divide degrees into arc minutes. There's 60 arc minutes in a degree. We divide an arc minute into 60 arc seconds. 1 arc second is the equivalent to observing a euro coin at 5 kilometers away. So these are really tiny angles you're trying to measure. And up to the 19th century, instrumentation just wasn't good enough to do that. But that all changed as the telescopes and other measuring instruments began to get more precise and allow measurement of this really tiny angle. And in 1838 or thereabouts, Friedrich Bessel in Germany was the first to achieve a fairly good figure for the distance to a nearby star. Basically, they initially used stars that they knew were traveling with respect to the background stars at high speed. And by observing those particular stars, it implied that they were close by. Therefore, they knew that they could use them to derive distances. And they come up with, like for 3 stars almost simultaneously, 3 observers independently came up with distances to them, but Bessel was the first to publish and is now recognized as the first to derive the distance to a star. Now that they began to work out distances to stars, they could then determine how close, if they brought them all to a similar distance, the ones that they measured. Up to the end of the 19th century, they'd measured the distances to about 65 or 70 stars. So they started looking at what if all these stars were at a similar distance, and how bright would they appear then? The distance that they used to determine this was 10 parsecs. In other words, a star, the angle it would appear to jump back and forward by against background stars is, if 1 arc second is equivalent to 3.26 light years, 10 parsecs is 32.6 light years. It was adopted and called the parsec, but the name was first proposed by Monk, who measured the deflection of starlight in Earnsford Terrace here in Dublin. But the name is generally credited to someone else rather than Monk, who independently proposed the name. But certainly that measurement of bringing all the stars to a similar distance allowed us to develop a new way of measuring brightness, and that was called absolute magnitude rather than apparent magnitude. Apparent magnitude is what how bright an object appears to be when we look at it in the night sky. Absolute magnitude is if we brought all these objects to the same distance from us. And this graphic really demonstrates that clearly. Sirius, the brightest star in the sky, is bright because it's close to us. It's 8.6 light years away. So if we move it out to roughly 4 times that distance, or 10 parsecs away, and brought all the other stars that are part of the constellation of Canis the Major, the Greater Dog, close to that 10 parsec distance, they'd all outshine Sirius in the sky. Our own sun, if we put it out to 10 parsecs away, would kind of be a little bit fainter than what Sirius would look like there. So we'd be a pretty insignificant star in the night sky of some observer around the planet 10 parsecs away. But and certainly that allows astronomers to start determining the properties of stars. Once you bring them all to a similar distance, then we start getting into the area of quantifying star brightness in a different way. Nowadays, professional astronomers tend to talk about luminosity rather than brightness. Luminosity in terms of what's the intrinsic brightness of a star compared to our sun. If we take our sun as a value of 1, how bright are the other stars compared to that? How luminous are they? Luminosity, as a definition, is the amount of energy emitted by the star per second. And apparent brightness even has been redefined in a more mathematical way than the way amateur astronomers use it. In professional astronomy, apparent brightness is the amount of energy per unit area per unit of time falling on a detector such as a CCD camera. And that allows a much more precise measurement of apparent brightness. Luminosity can be interchanged with absolute magnitude, but in professional astronomy, they tend to disregard the term absolute magnitude because it's not mathematically quantifiable. It's a unitless measure in essence. A true measure is based on the amount of watts being output by an object. This all led ultimately to the development of the HR diagram, or the Hertzsprung-Russell diagram, probably one of the most famous diagrams in astronomy, where you can quantify a relationship between how luminous a star is and what temperature it is measured in Kelvin. Initially, like a spectroscope essentially analyzes the fingerprint of a star. The fingerprint of a star, like every star, is made up of many chemical elements, each emitting, radiating at different energy wavelengths. And when you look at a rainbow, for example, like a droplet of water is splitting sunlight into its visible constituent colors. When we look at a star, we're also doing the same. We're splitting its light into the constituent colors. But when you look at the spectrum of a star, it's crisscrossed by many lines. Each individual element has a fingerprint or a signature that's it's radiating energy at, and you can classify the composition of the star according to that. Initially, the spectra that were taken at Harvard, tens of thousands of spectra, were classified by Wilhelmina Fleming into a sequence of A, B, C, D, E, F, and so on, based on the strength of the hydrogen line in a star's spectrum. But it was soon realized that some stars, the hydrogen line was weaker even though they were hotter, or it was weaker because they were cooler than reference stars. That's because in a really hot star, hydrogen is being stripped of its electron in its photosphere or the outer layers, and ergo the amount of energy being radiated by the hydrogen atom itself is much weaker than a standard hydrogen atom. And in a cooler star, atoms like to stay at their lowest basic state, or as someone once said, atoms are lazy. They don't like to be excited and kicked about. And in a cool star, there's very little activity going on, so the spectrum will show weak hydrogen lines. And as a result of that, the computers at Harvard decided to reorganize the sequence of letters that they had, and instead reordered it based on the star's temperature. Stars are perfect emitters of thermal energy. The color of a star is very much dependent almost solely on its temperature, not on its chemical composition. And the higher a temperature, a star can also be called what was called a perfect black body, or based on Planck's law. The curve of the Planck curve or the black body curve of the star peaks at certain energies depending on its temperature. The hotter a star, the peak is much higher and it appears bluish. A star like our sun It's peaking in the yellow-green part of the spectrum, and a cool star is peaking in the red part of the spectrum. And based on that, so if you can imagine a load of blackbody curves overlaid here, just all peaking at certain points, going from left to right across the HR diagram. And based on that, Hertzsprung and Russell independently found that by plotting the stars that they were observing, well, in this particular sequence, what's called the main sequence, where you find about 90% of the stars in the sky, but there are exceptions. A star that's in the main sequence, for just to be confusing, it's called a dwarf, as distinct from white dwarfs, which are small but very hot stars where the outer layers have been stripped away just to leave the hot core. And then the giants and supergiants are the ones like Betelgeuse and Antares, Aldebaran, where they've evolved off the main sequence, but are extremely luminous because they're quite massive. Again, based on another law called the Stefan-Boltzmann law, two stars that are of equal mass, but one is twice as hot as the other. The hotter star will radiate 16 times more energy than the cooler star. And that's also how you end up with the really hot stars being super luminous, because even though they might be similar in size to other stars, because they're extremely hot, they're radiating much more energy than the cooler star. But then a star can also be really luminous because of its size. The bigger a star gets, the more surface area it has, the more energy it's radiating into space. And that's why you get the likes of Betelgeuse and Antares to the top right of the graph being extremely luminous, but that's purely because of their sheer size. Antares, for example, would stretch out beyond the orbit of Mars if it was plonked in the middle of our solar system. So that just gives a quick overview of some of the astrophysical quantities. But onto the stars themselves. Well, if you were out observing on a clear night this month, you'd see almost half of the first magnitude stars visible from Ireland in one particular area of sky. It's an area that there can be joined up by this hexagonal shape. It's been dubbed the winter hexagon. It encompasses the stars in Orion, Canis Major, Canis Minor, Gemini, Auriga, and Taurus. And all of these stars are bright for a very good reason, because they're kind of in our backyard, so to speak. Our solar system is about 2/3 of the way out from the center of our galaxy, the Milky Way. And our solar system lies in an arm of the galaxy, sometimes called the Orion Arm, but more often the Orion Spur. It's an offshoot of the Perseus Arm, which is one of the major arms of our Barrett spiral. And in that region, we're seeing like stars like Sirius, which are nearby, but also stars in Orion are bright because they're quite young. They were born in a general region of space that in an area called so it's the next slide. The Orion Nebula. The whole of the constellation Orion is wreathed in nebulosity, showing that it's a region of intense star formation that's still ongoing. If you look at the Orion Nebula through even binoculars, like larger binoculars or a telescope, you can see the trapezium stars, which are quite young stars, but are lighting up the gas from which they've formed. This whole area and all around the sky, there's bright star-forming regions that appear to be linked by what is called the Gould Belt. It was first observed by Herschel and then further observed by Benjamin Gould from Argentina when he was based there. And it appeared to be a ring of bright stars going right around the sky that were essentially encompassing many star-forming regions, but also tipped at about a 15-degree angle to the general plane of the Milky Way. In more recent years, it's found that this just seems to be an effect of perspective. And in fact, the Gould Belt is more like a long linear wave, about 9,000 light years long, that is nearby to our solar system. The closest part of it is up here in the Taurus molecular cloud. It's about 400 light years away, and it extends right up to the northern part of Cygnus and a distance of about 5,000 light years away. But this Radcliffe Way required the development of the Gaia satellite to really begin to unearth its true nature. They now believe that our solar system actually crossed through the wave about maybe 14 million years ago. And there's a strong possibility that it may have caused a dimming of the sun then. But it'd be very difficult to find that in the geological record because any evidence would more or less be potentially obliterated at this stage unless they come up with techniques of determining just what effects there would have been, rather like how they found in the K2 boundary layer higher concentrations of iridium to try and tie it to the demise of the dinosaurs from an asteroid impact. But the Radcliffe wave is somewhat associated with the Gould Belt, but there's a number of other linear features nearby as well, and those combined, from our perspective inside this feature, makes it appear circular rather than linear when you fold it out and spread it across the sky. So it's quite a fascinating, but as you can see, it does encompass a lot of star-forming areas, the Pleiades, going up to like the OB associations in Perseus, the double cluster into Cassiopeia, Cepheus, and on into Deneb, and the regions there, like the North American Nebula. Sirius, I mentioned, is about 8.6 light years away in our backyard, so to speak, in a region called the solar neighbourhood. And in fact, if we do a survey of nearby stars, we find the vast majority are quite small, more or less much smaller than our sun, classed as red dwarfs. These are the most common types of stars. The universe doesn't like making very big, massive stars because they're inherently unstable have short lifetimes and end their lives spectacularly in a supernova explosion. A smaller star, on the other hand, carefully husbands its nuclear fuel. A red dwarf, for example, has a lifespan of about 1 trillion years. That's longer than the age of the universe, much longer than the age of the universe. And these stars go quietly about their lives, well, sometimes, but but if you look at the distribution of them, they are in the majority, whereas in a volume of maybe 1,000 light years of space, you'll only find a couple of really massive stars, because they don't live very long. And the only other, we've only a handful of other bright stars in our sky that just happen to be nearby. The others, like the stars in Orion, like Betelgeuse, Rigel, are bright because they're massive to begin with. They're huge stars, or else they're shining at tremendous luminosities, like Rigel, outputting huge amount of energy. Arcturus, Spica, and Regulus are springtime stars. They're interesting in their own right. Spica is a close binary star. Regulus is made up of 4 stars all orbiting very near each other. Also Regulus is a very fast spinner. If we saw Regulus up close, it would be almost egg-shaped, distorted into oblate, like squash, like a rugby ball, because its equatorial region is being flung outwards. And that spin is basically imparted from the initial nebula from which it formed. It'll never fly apart because it's not going to speed up. Only in very rare cases, if there was another nearby star in the system, might it impart more spin to the star and maybe cause it to start tearing itself apart. But this generally never happens. The spin is really based on initial imparted spin. Arcturus is probably my favorite first magnitude star because there's so many stories behind it. For example, the World's Fair in Chicago in 1933, I think, they used the light of Arcturus to turn on the illuminations for the World's Fair. They focused its light onto a photoelectric cell and turned on the fair lights, because it was believed to lie about 40 light years away, and the previous World's Fair in Chicago had taken place 40 years prior to that particular one. Arcturus is about 37 light years away. But Arcturus is interesting in another sense, in that it's a so-called halo star. It's diving perpendicularly down through the plane of the Milky Way, traveling in from an area known as the thick disk. The thick disk is about 4,000 light years on the side, and these are older stars that are basically not following the general flow of traffic around the center of our galaxy. Like, our solar system is in the thin disk, which extends for about 250 light years above and below the plane. And you'll find the vast majority of the stars in the Milky Way in that region. But a thick disk star like Arcturus we're just encountering it now, but it will fade from view as it passes by our neighbourhood, and we'll likely never meet it again on our travels around the Milky Way. It's not known if it ended up there from maybe a dwarf galaxy or globular cluster that strayed too close to the Milky Way and got shredded. The stars that were members of that object would have been torn out and drawn out in a long line, following an orbit, the original orbit around the Milky Way that the globular or dwarf galaxy took. The other possibility is that it could be a member of a stellar association. We know that Arcturus is accompanied by about 35 other stars that are showing a similar orbit and direction of travel. Arcturus could therefore have come from a cluster that stellar associations are generally the outlier members of an open star cluster. They're much more loosely bound gravitationally to the cluster, so they tend to get torn away from the cluster first by the gravitational influence of our Milky Way. And Arcturus may be the relic of a cluster that once existed, or maybe has drifted away somewhere else around the galaxy and that we can't see. But it's one of those stars that is a familiar sight, and one that's worth learning a bit more about. It comes up as well just after the bells toll for New Year's Eve. Like, it rises just after midnight, so I often like to see it as the herald of a new year ahead. Coming into the summer now, Antares, I mentioned, if we plunked it into the middle of our solar system, it would extend out beyond the orbit of Mars. It never gets very high from Ireland's latitude, but it's quite distinctive. If you're up in the early morning hours, maybe an hour or an hour and a half before sunrise, these mornings, you should see it coming up. We're still kind of in winter, but yet seeing Antares hopefully is a highlight of warmer days ahead. Summer Triangle is actually visible well into the winter, and Vega, the brightest star of the Summer Triangle, is circumpolar. In other words, it never sets from Ireland. In fact, it's roughly the same distance from Polaris as the star Capella in Auriga. So when Capella is low on the horizon, Vega is overhead, and they swap positions over the course of the months. And when we come to the late July, August, you'll see Vega almost directly overhead and Capella low on the northern horizon. So they kind of trade places. They're roughly similar distances on the celestial sphere from Polaris. But one of my interests is mythology of world cultures, and in fact, one of the most famous stories in Chinese myth is the story of the weaver girl and the cowherd, and they heavenly maidens came down from heaven. They were just by a river. They were spotted by a cowherd who fell in love with the youngest and fairest of them, and her sisters went back to the sky, but she stayed behind, and the two eventually got married, and they had a son and daughter, which are the stars either side of Altair. But the heavenly maiden's mother didn't really approve of all this, so she ordered her back to heaven, and she reluctantly returned to heaven. The mother took her silver pin from her hair, drew a slash across the sky, which became our Milky Way, which divides the two stars. And in fact, Milky Way does flow between Altair and Vega when you see it in the summer sky. But on the seventh moon in the seventh month, or the full moon in the seventh month of the Chinese calendar, all the magpies of the world come together and form a bridge over the Milky Way and allow the two lovers to meet once more. So but a nice myth, and one that you can maybe next summer, if we get clear night, you can But quite near Vega is what's called the solar apex. That's essentially the direction of travel of the solar system as we go around the galaxy. We might appear to be standing still, but the sun and everything orbiting the sun is pushing through space at 800,000 kilometers an hour, zooming around the center of our galaxy. It takes about 225 million years to orbit the galaxy, but that's the general direction of sky we're going in. And so it's quite nice in the spring months to stand in an open landscape, and the solar apex is not very far above the horizon at this time of year. So when you look in that direction, we're looking in the direction of travel of our solar system. In fact, that's why we're seeing these objects like 3I Atlas and Oumuamua a few years ago, these interstellar objects that came into the inner solar system. We're essentially meeting them head on. When their trajectories are calculated, they appear to come from that direction of sky. So they're not spaceships. They're just essentially like a car driving through a cloud of flies. We're just sweeping up these objects as we zip around the Milky Way. We're just getting better at detecting them. And in fact, Vera Rubin, when it begins its survey of the sky, will almost certainly pick up more of these. So it's either Avi Loeb's invasion fleet, or we're just finding more rocks as we're swatting them aside as we go around the galaxy. If we look at the stars themselves, they're Deneb is a huge star. Where if it was as close, like when I mentioned absolute magnitude, the distance, if all stars were at the same distance, if we brought Deneb that close, it would cast shadows on the Earth from 32 light years away. It's truly a huge star. In fact, we're not even sure how far away it is. You'll see all sorts of guesses or guesstimates as to how far away it is. The problem is that it's too bright to measure with the detectors on the Hipparcos satellite and on the Gaia satellite. It would saturate their detectors, so they don't actually look at it. Now, there is a suite of nano satellites that went up in the last year or two, which are starting to look at the really bright stars and get a true, try and work out a true measure of their distance. Vega was often called the 0 point star because it was considered to be exactly magnitude 0. And at all, it was it, along with similarly bright stars, which that appear to be unchanging, would become the reference stars. Unfortunately, stars don't adhere to what we want them to be, because when we look at Vega in other wavelengths of light through other filters, the filters only allow through a single wavelength of light. And there's a certain standard set of filters that astronomy instruments use. We find that Vega is very slightly variable. We also find that it's surrounded by a cloud of dust, so that means it's bright in the infrared. So brightness has to be quantified based on the filter you're using to observe it. But brightness can also change depending on the instrument you're using, because it's very much, you're trying to standardize a lot of components of the system you're looking at the star. Altair is another fast spinner. It's again distorted into that egg shape because of its the bulging out at the equator. Like myself. And then we're coming near the end. Fomalhaut, often called forlorn Fomalhaut, because it just seems to be out on its own in a bright star core area of sky, easily found by dropping down from the right-hand side of the square of Pegasus, low on our southern horizon during the autumn months. In fact, it's the most southerly first magnitude star on the celestial sphere that we can see from Ireland. Just slightly shades Antares for that distinction. Fomalhaut is quite interesting because when it was observed in 2008 by the Hubble Space Telescope, it was believed to have had a planet orbiting around it within a dust disk that surrounds the star. It was observed over a number of months, and then it disappeared. And it even got dubbed Fomalhaut B, but it was extremely puzzling as to what happened to it. And they subsequently began to theorize that it may have been a couple of asteroidal bodies that collided with each other and briefly caused a brightening of that area of the disk. And it gradually faded over the following few years. But yes, just the last few days I've read that they think there might have been another asteroid collision within the disk. They found another brightening in the disk recently. I haven't read the full article yet, but I think it's on universetoday.com that I saw it. But this disk, like all planetary disks that we're finding at the moment, are where will ultimately accrete into new worlds, new planets, and possibly new life. The interesting thing about this, when we look at this time of year as well, we also are looking up to, well, in the sky, we're looking up towards the Andromeda and then the Andromeda galaxy, but in reality, we're looking down. If you take it in the context of the orientation of the solar system, our solar system is tipped over on its side. And in fact, you look in astronomy books and the solar system is a nice flat plane on the page, but in reality, our solar system is tipped over and the sun is going around the galaxy like that, with the solar system being carried around. So as the Earth orbits the Sun, we're up here during the spring, so we're looking up and out of the plane of the Milky Way galaxy. And during the autumn, we're down here looking below the plane of the Milky Way galaxy. And that's clearly demonstrated in this diagram, where at the Andromeda galaxy, we're looking down at it, even though it's up in the sky from our perspective, and the Triangulum galaxy. And then in the spring months, we're looking up at the constellations of Leo, Ursa Minor, Draco. So next time you're out, it's quite interesting in your mind's eye. Try and picture in reality what's our orientation with respect to the universe. And hopefully that quick tour of the brightest stars will give a new perspective on when you next go out and observe. And I guess a few books on the subject are those ones there, like Patrick Moore's Brilliant Stars is in the Society's library. These other ones, this one not as good as it would promise to be. It's trying to cover too much and too much detail. But these other ones, plus looking online, you'll find a lot of interesting articles on the subject of not just the stars themselves, but on the concept of magnitude and brightness. So thanks very much, everyone.